The INRIA research team eMotion and Chroma work on reasoning and perception of mobile robots using Bayesian methods. These mobile robots operate in dynamic environments, complex and populated by humans. This is Christian Logier, research director, who presents the work of the team in terms of smart vehicles. Actually, today's vehicles work well. We see nice demos, but there are some cases where it doesn't work very well. We've got a lot of misperceptions when we've missed a pedestrian or made a decision about the system that was not quite right. Our approach addresses the difficulty of system robustness, perception and decision. And for this, we use probabilistic models, especially the so-called Bayesian models. For this, we represent space with a probability grid with two values. A first one which represents the probability of occupancy, and a second one which represents the probability of velocity, in order to adequately represent the dynamics of space. Once we have these models, it requires us to reason about these models, and it means that we have an interference mechanism that allows us to take into account a temporal space, since we reason on the dynamics. So we will have to take into account the past, the present, and the future. From these models, we're able to raise ambiguities because we have much more information when taking an image sequence rather than a single image, so we will remove these ambiguities. We have information on the dynamics of movement, and so we'll be able to make predictions at 1, 2 or 3 seconds, what will probably occur in that environment, and this is typically what all human drivers do. Another feature of the system is to be embedded. It means real-time constraints, size constraints, power supply constraints, and also system reliability constraints. So we work on these techniques and miniaturize everything we can. On cars, for example, we often see a car boot full of electronics and calculators. The idea is to replace it with a simple electronic board that can do this processing from an algorithmic perspective. It also has functions that are highly parallelizable. Another important property of this approach is to allow predictions which are extremely important to make good decisions in such environments. We make short-term predictions, that is to say from 1 to 3 seconds. It defines what are the most probable movements of mobile entities of the environment and predicts the risk of collision, and thus helps us to make the right decision. It can also be the medium-time predictions, up to maximum 1 minute. We did exactly the same thing, but with more accurate models as role models on mobile entities or template movements. We've actually done things like this, for example, with Toyota and Renault, and they were patented. There are several possible applications for the industry. The most important for us are those that currently aim to assist driving more and more effectively, and the others to have systems that are becoming more independent. As they say, the autonomous driving in certain circumstances.
La conduite autonome, dans certaines circonstances. Other
types of applications include other types of mobile robots. For example, an automated wheelchair for elderly or disabled people. Or small vehicles to move people in large industrial, complex environments, in airports or in amusement parks. Another type of possible application is to increase capabilities of today's industrial mobile robots in order to be more interactive with the humans who are present around them.